So what we're going to do now is we are going to change that reference frame. So far we've been working in Cartesian components, and now we want to go to radial components. And just like what we saw in our kinematics equation, we want to go to that reference frame that's going to work best for us. So why? Kind of think circular motion, think roller coasters, think curves, think planetary motion. And we want to look at that same thing that where we could develop the path and look at that path as arcs of various circles, just like what we saw in kinematics. So we want to see that, to do that in terms of curves. And I want to kind of remind you about the kinematics of circular motion. So I'm going to go ahead and replay this little video here. And so we're using the animation to help us out and look at the vectors. And we've got our velocity vector always tangent to the circle. And so remember, we're going to get an acceleration because we get a changing velocity. And now we get that centripetal acceleration. Now remember, this is the instantaneous acceleration, and as we go through a different path, we are going to also have a tangential component as well as that centripetal component. So just kind of remember the visualization that kind of helps us out and looking at where we want to go. So now, when a particle moves along a curved path, it may be more convenient to write the equation of motion in terms of that normal or that centripetal, if I'm in a circle, that part that's going towards the center, and the tangential component. So remember that we can do it in terms of our two components. Now, of course, we're dealing with our summation of forces, right? So I'm going to have my summation of forces is going to be my tangential force, my normal force, and plus this B force that may be perpendicular to our curve, right? That may be perpendicular to our curve. But if we're traveling along a two-dimensional path, we're not going to have that U of B component, and so I am not going to have a mass times acceleration there, and that force component is going to go to 0. Remember that my tangential component is going to look at my velocity with respect to time, and my normal component gives us back that v squared over r, but because I'm now dealing with a radius of curvature, I can do this in terms of my radius of curvature. So now my force in the normal direction is related back to my centripetal force. Like, well, all we've done here is if we've expanded our path to be along a curve versus looking at it just as strictly circular motion. So that hopefully should help, but we want to also remind things that the normal direction always points towards the center of curvature, just like in my centripetal motion, and we always have that center of the circle. The tangential direction is tangent to the path and is usually set as positive in the direction of the motion of the particle. So when we're solving problems with using that normal and tangential coordinate system, we're going to use the coordinates when the particle is moving along a curved path. We're going to establish that normal and tangential coordinate system we're going to draw our free body diagrams and look at that. Remember that our normal acceleration is pointed inward towards the center of our circle or into the path. Our tangential is going to act in either the positive or the negative direction, and we generally assume that the tangent is going to be positive in the direction of the particle. And then we'll apply our equations of motion in our scalar form and solve, but we may be necessary to employ our kinematic equations. So don't forget that my tangential acceleration looks like my velocity derived with respect to time, or I can put it in terms of its individual x component or y component. And finally, just for reference, we're going to bring back that radius of curvature expression. If you need to go back and look at where that radius of curvature comes from, go back to last week's lectures and you can find where that radius of curvature has come from. So hopefully to make this make a little bit more sense, let's look at a couple example problems. So I have a merry-go-round here, and we have a girl sitting at the edge of the merry-go-round. So this is going to be a typical circular motion problem, much like what we would have had in general physics. And we've got a 25 kilogram girl sitting on the edge of the merry-go-round. We're going to make an assumption that we're going to go around slow enough that we don't have to deal with that tangential component of the acceleration. Again, this is very much like that original circular motion problem that we saw in general physics. We want to determine the maximum speed for the merry-go-round before the girl slips off, and we're going to assume that the coefficient of friction between the girl and the merry-go-round is 0.3. So we're going to look at our normal component of the force. We're going to calculate the force due to friction, and the girl is going to slip at the instant that my force due to friction is equal to the summation of forces in the normal direction. So we can go ahead and put this in terms of our v squared over r. We're going to rearrange to solve for v squared. We've calculated our force due to friction. We know what the radius of curvature is. We know the mass of the girl, and we find that v squared is 4.41 meters squared per second squared. Take the square root, and we end up with 2.1 meters per second. So it's very similar to what we've seen in the past, and we're just dealing with that circular motion piece. So now let's take it one step further. Let's do that traditional swing ride that we see at the carnival, right? This is our carnival swing ride. And if you want to look at it in the Hibbler book, it's chapter 13, problem number 65. So we've got our swing here, but let's look at it from a sideways perspective so that we can actually draw a few things. We're going to have the tension in the rope. We're going to have our acceleration or our force drawing it in towards the center, our centripetal acceleration. We're going to have our force due to gravity, and in our normal component, it's just going to be our circular motion piece. But we're going to have to know how far away we are, right? We're going to have to know how far away we are. So we're going to use some simple geometry to find out where that is. Our bar of our swing side, our swing ride is 4 meters. We're going to have to deal with this. We know that this is 6 meters. So we're going to need this little space here on our triangle. It's 6 times our angle. And so we are actually given in the problem that we're going to be at 30 degrees. That's coming from the problem in and of itself. And so we can find that the tangent, or we can find our radius. And so now I've got to have what's the force that's being applied in the normal force. It's my tension, my normal force component of my tension. So it's the tension in the rope times the sine of 30 degrees. We're given that our mass is 80 kilograms. We don't know the velocity squared, but we do know r. So we're going to take this a step further and use our other equations to help us get there. And in this case, we know our normal component is there, but now let's use our y component, our summation of our direction in this direction, and we can solve for our tension. Then we can go back in and plug it in there, and we get the normal component of the weight of the passenger, and we get our v squared component, and we can solve for the two different pieces. So I encourage you to go back and actually read what the problem says, and I will do that here so that we can have it in our piece. It says determine the constant speed of the passengers on the amusement park ride if it is observed that the supporting cables are directed at an angle of 30 degrees from the vertical. Each chair, including its passenger, has a mass of 80 kilograms. So that 80 kilograms is the mass of the passenger plus the mass of the chair. And also determine the components of force in the normal, tangential, and B directions, which the chair exerts on the passenger during the motion. So that's where this part of the problem comes in. It's the forces on the passenger from the chair. So this one we brought in that B component. So sometimes cylindrical components make a heck of a lot more sense in order to deal with it. So when we, just like what we saw in kinematics, we had our circular motion piece, and then we brought in that cylindrical motion piece. And it also may make more sense to work in your terms of R and theta. So this will give us another way to handle it, but the path may be complex, and so we want to do our R and theta. So just as we saw in our kinematics, we can rewrite our acceleration due to R in terms of R and theta, where we've got our second derivative and our first derivative. We can do it in terms of our theta, just as we saw in our kinematics equations. And because these are cylindrical components, we've got it in terms of our Z as well. So if the particle is constrained to move only in the R theta, we can get rid of that Z component, and we only have to deal with the first two components of the R and the theta component. And for a fixed coordinate system, it's not body-centered. We use the normal and tangential approach. This may make more sense if we're using the body-centered, then the normal and tangential approach may make more sense elsewhere. So let's look at our normal and tangential forces. So we've got our particle. It's traveling around an arc. And we've got a force P that's causing the particle to move along this path. The normal force is going to be pointed towards the center of the curvature, and the tangential force is going to be applied along the edge. The frictional force always acts along the tangent, okay? So if we've got to bring in friction, it's going to act along that tangential motion. And the directions of the normal force are specified relative to the coordinate angle, and we can get this strange angle phi that we want to look at. And we can determine phi by just doing a few calculations here and doing our triangle. We've got our radius, we know where our phi is, we can get our little d of r, and we have our change in our angle. And so we can kind of go through the analysis to get us at the tangent of phi is r d theta over dr, or r over dr d theta. So we have that component. And if phi is positive, it's measured clockwise from the radial line. If it's negative, if it's positive, it's measured counterclockwise. And if it's negative, it's measured clockwise. Think about where we're going to go when we start bringing in rotational motion and start bringing in our torques. We're going to need to be in that clockwise and counterclockwise sign convention. So to help us with this, I've got another example. This one happens to be a roller coaster problem, and it's 1399. And let me read it to you so that you have it as well. Give me just a second. All right, a car of the roller coaster travels along the track, so we've got that set up, which for a short distance is defined by a conical spiral, given that r is 3/4 z and theta is equal to minus 1.5 z. So we've got our track is defined by this r, and our theta is defined here. R, z are in meters, and theta is in radians. Remember, when we're doing this, we want to be working in radians, and we're given that and it also says that theta dot, is going to be in 1 radian per second, or our angular velocity is in 1 radian per second, is always maintained. We want to determine the r, theta, and z components of the reaction exerted on the car at the instant z is equal to 6 meters. And the car and the car and the passengers have a total mass of 200 kilograms. So let's look at what we have on the car, because that's what we were wanting to find. We're going to want to find the forces on the car. So I have my z component, I have my r component, and I have my theta component. We've given the mass, so we're going to need to know the normal force, or the weight, and the weight is 1962, and it's in the z direction. We're going to go ahead, just like what we did before. We're going to find our r components, our r dots, and our r double dots, and we're going to find our theta dot, theta double dots, and our z dot. So we can go through all of that so that we can get there and go through all of that, and then we can, once we know our values here, we can plug in, and we know that this is equal to 1, right? We're told that this is equal to 1, which allows us to solve for our RZ dot. So we get this right here because we were told that this was given, that that's a constant. And since that's a constant, this has to equal 0. So that's where we end up all the way through here, that we want to make sure that we get our z dot. So we can go back in and plug in when we have z is equal to 6. We solve for it, so we can solve for our tangential component, we can solve for our normal component, then we can solve for our various forces. So you can go through all of this and remember that we've got those different pieces here, and you can solve for these equations. I'm sure I'm going to have some more examples for you, but hopefully this gets you through the rest of chapter 13. We're going to start chapter 14 next time.